In part one, we left off with this slide, and what we discussed was the difference between the reference electrode and the indicator electrode, and that the difference in those voltages would give us the voltage across the cell, which would be the concentration or lead to the concentration of that specific electrolyte in the analyte. Essentially, we have to talk quickly about the voltage measurement strategy and realize that an ideal voltmeter has an infinite input impedance. And what that does is that draws zero current from the circuit under test. And I believe this was discussed in lectures earlier in this course. So by drawing zero current, there's actually no impact on the circuit as the voltage is being measured. So the more current draws from the circuit under test, the more the measured voltage will sag under the loading effect of the meter. This is similar to a tire pressure gauge releasing air out of the tire being measured. The more air released from the tire, the more the tire's pressure will be impacted by the act of measurement. So the technique of potentiometry involves the measurement of cell potentials under conditions of no current flow. I mentioned that in the last video and earlier. In the electrochemical cell, if a high impedance device, like a voltmeter, is placed between the indicator and reference electrodes, no current will flow between the two compartments. There's an assumption to be made here. In order to determine the indicator electrode's potential from the cell voltage, the potential of the reference electrode is assumed to be constant and independent of the composition of the sample. This may not always be true. The physical and chemical phenomena on the phase boundary of the reference electrode is the same as the indicator electrode. However, maintaining a reference electrode independent from the potentially complex sample composition is not necessarily trivial. So note that if the potential of the reference electrode changes with the sample composition, it introduces an error in the determination of the indicator electrode potential and consequently the ion activity that is calculated from the indicator electrode potential. This error is a reality of measuring complex samples, and we're just mentioning this just as really as an FYI, and it's not going to be something we look at very closely as we move forward. So it's just mentioned as one of the potential errors that could occur. As a practical matter, it is quite challenging to theoretically compute the potential difference between the indicator and reference electrodes using first principles. Many papers describe the process, though it is outside the scope of the current presentation. More relevant and considerably simpler in the near term is to recognize that the Nernst equation suggests the potential difference is proportional to the logarithm of the ion concentration. If you go back and look at the diagrams, you see that the logarithm was used in those concentrations. This leads to the following steps for calibrating an ion-specific electrode. First, obtain a calibration curve for a known ion by preparing several known concentrations, collecting data on cell potential and concentration. And actually, you'll probably do this as part of the pH project we'll talk about later on. Then, create a plot based on the measured potential and logarithm of the ion concentration. Then it becomes a linear, right? So based on this plot, assume a near linear relationship and estimate the coefficients of the approximate Nernstian response. Kind of a simple, clever method for creating a really sort of a calibration curve for concentration. Let's see how the calculation of the linear relation works in practice. In this case, we're going to do the determination of a fluoride ion concentration. Fluoride is added to drinking water and toothpaste to prevent dental caries, and its determination of its concentration accurately is of great importance. Staying within specified limits is very critical. Calibration data for the electrode is shown in the table below. And what we want to do is, in this case, determine the relationship between measurement potential and fluoride concentration. Well, of course, we have our table, and of course, we got the concentration of milligrams per liter. We take the logarithm of that, as we described in the previous page, and this is the corresponding voltage. When we plot the voltage as a function of the concentration, we see that we really basically end up with what seems to be a straight line. And actually, the result is very easy to obtain. It's just a linear regression correlation, and it's shown here that the voltage is the sum of the 100.59 minus the slope times the log of the c. high correlation factor. So essentially what happens is really simple. You take your data, draw a straight line by manipulating variables in a very trivial way, and then you end up with this linear relationship. So whatever the concentration is, all right, that'll tell you what the expected voltage is, and you can actually flip this around too. If you have a certain voltage, then you can figure out exactly what the concentration is. Kind of a clever thing, pretty straightforward, simple algebra. I didn't really go into detail about how the linear regression was performed, and quite frankly, there's really many software options, and it really doesn't matter what your preference is. You could use Python, you can use R. I prefer R sometimes for my statistics, but Excel works just as well. So the fluoride analysis in R is very similar to many other calibration scripts, and as you can see in the calculation, it's really pretty straightforward. Most often, it's really not the calculation that's important, it's the interpretation of the results that's a challenge. So this is just a simple program, and again, a very, very simple example on how you can take some test data and then from that create a calibration curve that will allow you to determine, say, what the expected concentration is given a certain voltage that we obtained from the ISE. Another calculation is really the estimation of concentration and standard error based on regression. This is a little nuanced, and it's not the standard error that most people think about. But let's talk a little bit about that. So basically, we have an unknown sample, gave a response of 45.6 millivolts, and that was averaged from 4 repeat readings using a fluoride ion-selective electrode. So what we want to do is to determine the fluoride concentration and standard error for the unknown sample. The twist here is that we have responses from averaged from 4 repeat readings. And so basically what we have is, of course, we've got the concentration, we've got the log of it, and then we've got the voltage output. And then what you do is you actually do a simple regression. We've talked about this before, not a big deal. And the log of the line of best fit is y, is equal to 117 minus 63.9y. And of course, it's really easy to solve for x when y is 45.6, right? So there's your average value, 45.6. You plug it in here and you compute that x. And of course, we had used logs. So basically what happens is the x concentration is the 13.314. Now, the point we're trying to make here is that the standard error for the unknown sample based on a regression equation is not the standard measure in a typical linear regression analysis. Now, there's a paper I've posted on Canvas, and it's a interesting, if not challenging, math problem. But basically, there's a process for understanding the variability and computing the variability and estimated coefficients of a regression model, right? Estimated of the coefficients for a regression model. And so then what you do is you compute the standard error of the regression coefficients, all right, including the intercept and slope. Becomes a little bit detailed, so I've mapped this out, and we detail that a little bit on the next page. Continuing with the calculation, we're going to do the estimation of the concentration. Part 2 is that the equations for the standard residual error, shown on the right over here, can sometimes be very clumsy to work with, so computing with a package such as R is convenient. I provided the equations that you can use to compute the standard residual error of y, and then the standard residual error of the value regression, okay? Slightly different. You'll notice that the number of calibration samples is entered into the equation. Sometimes you don't see that, so it's a little bit different. And there is a reference for this. I believe it's posted on Canvas, and you can dig in there. But essentially what we're doing is just giving you the equations, and basically what you say is, for the current problem, the result is S of y is 1.43, S of x is 0.0159, so you do the logarithm, and what you end up with is the concentration is 13.38 plus or minus 0.049 millimoles. So that's again, it's a little nuanced, it's a little different than what most people do, but it's important when you're actually collecting data by taking averages of samples. It makes it the mathematics, again, is in the document that I believe is posted on Canvas. and you may want to dig into, but basically sometimes just knowing the equations to use and how to use and running the program to run it is probably enough for the scope of this course. As we wrap up part 2 of the video, just a few parting thoughts. Keep in mind the different methods involved in electrochemistry. There's basically 4 major ones. What kind of measurement is potentiometry? Of course, it's basically an equilibrium measurement. There's obviously differences in electrochemical methods. We focused a lot on the potentiometry method, and of course that relates to pH, which will be the subject of your project. And then ion-specific electrodes would be, your classic sodium, potassium, chloride, lithium, and calcium. Potentiometry is analogous really to water pressure PSI, measuring that. Whereas in amperometry, we measure current flow. And that's analogous to instantaneous water flow. And we'll talk more about that in a different presentation. Different forms of the reduction oxidation measurements. And something we should really note about current when dealing with potentiometry is in metal, the current is carried by electrons, and in liquids, the current is carried by ions. So a slight distinction there. Just a few things to keep in mind. To now summarize, basically, the ion-sensing electrode technology enables very selective electrolyte measurement. The ion-sensing electrode is fundamental to measuring many measurands, blood gases, electrolytes, metabolites. And essentially what I hope you got out of this second half video is that the calculations are greatly simplified through the Nernst equation that represents a potential difference between two sides of the ion-specific electrode membrane. Okay, thanks for your attention.